2 x minus a squared plus c sub 3 x minus a cubed. So you see, it's what we just did, isn't it? Except we're subtracting something now. So if I write this in its general form with the sigma notation, I have c sub n still, but instead of x to the n, x minus a to the n. And I think if you look at it this way, you can see it's more like that shifting, right? The minus a in here. So now that I've given you this, the first time I showed you power series, what was a? A was 0, wasn't it? A was 0. If you look back on the definition of power series, first time I put it up on the board, I actually was letting a be 0 in this formula. So if a is 0, that's just x, x squared, x cubed, right? But by having this general power series, we'll be able to move it around left and right. Now, can you tell me right now what would happen if x equals a? What happens to this series? If x is a, this thing converges, doesn't it? Because it actually doesn't add anything up. If x is a, that's 0, that's 0, that's 0, and all we're left with is that constant, right? Do you agree with that? So it converges. Where does it converge to? It actually converges to c sub 0. It is c sub 0. It's just a constant. So again, think of it more like that functional idea. If this is a function, if I define a function to be this, then if I tell you to plug in a here, are you going to get an answer? If I say replace x with a, are you going to get a numerical answer? Yes? No? Yes, you're going to get c sub 0, right? So it would be defined there. It would be defined at a. What if x isn't a? We have no idea what will happen. We don't know. We don't know if it's going to converge or diverge. We don't know. When I say, I'm talking about converge versus diverging. I have no idea if a general power series will converge or not if x is not a. If x is a, I guarantee you it's going to go to a number. So what we're going to do now is we're going to look at some power series, and we're going to try and figure out whether or not they converge or not. All right? We know that they're guaranteed to converge if x is a, but in general, we have to always check if x is not a. All right, so here's our example. All right, how about sum n equals 0 to infinity of n factorial times x to the n? What I'd like to know is this. For what values of x does this converge? Can you tell me right away one value for sure that you know it converges? Try and see this formula. Try and see this formula in there. Do you see this there? What's c sub n? Good, n factorial. So this is no longer that little wimpy geometric series where the c sub n was 1, 1, 1. That number in front keeps changing, right? Now, do you have x minus a to the n? Yes? What's a? A is 0. So is there a value that you know right now for sure this thing converges for?
0.
X is 0, right? If x is 0, it converges. But it wants to know all the values. So we need to check when x is not 0. Make sense? All right, so how are we going to check it? Well, this is a series, isn't it? And how do we check to see if series converge? Well, you have a whole list of things on a piece of paper, right? But the one I said is most important now is the ratio test. So what I'm going to do now is I'm going to run a ratio test on this series. And I'm going to take the limit as n goes to infinity of the ratio of the n plus 1 term over the nth term. So what is the n plus 1 term? N plus 1 factorial times x to the n plus 1, yeah, over n factorial x to the n. Now, when we were running the ratio test in the previous section, we didn't have x in there, did we? We didn't. We have x now, all right? What do we want for this to be able to say converges? We want this to be less than 1, right? We want to be able to keep this thing less than 1. Then we can have convergence. So we're going to be asking ourselves, for what values of x will this thing converge? So let's just keep doing what we did before. We like the factorials. We love them because they peel off real nice. I can write n plus 1 times n factorial on the top. How can I rewrite that x to the n plus 1? X to the n times x all over n factorial x to the n. We get some nice cancellation here. And all we're left with is n plus 1 times x, right? Now, at this stage of the problem, I'm going to do something that I will do pretty much standard from here on out when I'm trying to figure out if a power series is converging or not. And that's, I'm going to separate the n's from the x's, which it already kind of is. N plus 1 I'm going to put here. And then the x's, anything that has x in it, I'm going to put next to it like this. So I don't want to put these together, like don't multiply them through. Now, the question is, can I control this? Can I keep this from becoming bigger than 1 or not? Right? Because I need to make sure this stays less than 1. So if you hand me an x, right? If you hand me an x to plug into this thing, am I going to be able to keep this ratio from blowing up? No. Because this piece right here, n plus 1, is headed to infinity, isn't it? And this piece right here is fixed. In other words, you're going to plug in some value for x, right? You're going to plug in a number, 2. If you plug in 2 here, 2 times this, boom, it's going to go to infinity, right? This is going to be bigger than 1 no matter what I do. Now, you could get around it if you let x be what? 0. But we already know it converges when x is 0, right? Right? We knew that already. We said, for what values would this converge? We said when x is a. Well, we know it converges at x is 0. But if x is anything other than 0, that number, you're not going to be able to wipe this out. Make sense? I don't care. You could pick any number you want. 0.000000000000001, right? This infinitesimally small number. I'm going to let this go to infinity. Eventually, this is going to overrule this because that's stuck. It's fixed. Is there a question more? No? So what happens here? It diverges, right? So for what values of x does this converge?
0.
X is 0. Which is really kind of lame because that means if we were to define this as a function, all right? If I were to call this a function right now, everyone, the domain of it is a single number. And that's a very boring function, isn't it? Like if you graph it, I'm allowed to plug in 0, right? And if you plug in 0, you would get 1. You could check it yourself, but you plug in 0, you get 1. So here's what the graph of that looks like. It's a dot sitting there. That's it. Pretty boring. But what I can say is that I use the ratio test to confirm that that's what that is. All right? So let's do one that's maybe a little more interesting, right? Because that one, kind of lame. "10 minutes. Let's see if I can knock one more out here. Yeah. I'm going to do to you what I did to my other class. I'm about to make them suffer through one of these here. I'm going to introduce you to a function, all right? So I'm kind of giving you a hint already that this thing is going to have a domain that's more than just a single point. This is called a Bessel function. Anybody ever heard of a Bessel function before? So instead of writing f of x, I'm writing capital J subscript 0. This is called a zero-order Bessel function. And it is defined to be this infinite polynomial, or this power series, -1 to the n, x to the 2n, over 2 to the 2n, and then n factorial in parentheses squared. Now, we're about to show, we're going to have to run through it to show it. We're about to show, though, that the domain of this is all real numbers. That you can plug any number into this and it's going to converge. We have to show it with the ratio test. But if that's what our end result's going to be, then that means I should be able to graph it, right? And I've already gone through the trouble of doing that so that you could see it. And that's what I had up here before. This is the Bessel function. Now I've only gone between -20 and 20. It keeps going. But what the Bessel function is good for is modeling wave behavior, like if you drop a rock in a pond or something, and the way that the waves kind of dissipate over time. Or this even works for like a drum. You know, if you have a drum and it has some membrane on top and you hit it with a drumstick, I guess, right? Then the way that the wave on the actual membrane travels is modeled by Bessel functions. Now, they're different order Bessel functions. This is a zero-order Bessel function. There are first-order Bessel functions and second-order, and this changes. We're only looking at the zero-order. I believe the first order is in the homework assignment. I believe there is a first order. Yeah, it's number 29. The first-order Bessel function, you can show that it has a domain of all real numbers also. Okay. 7 minutes. I don't know if it's going to be enough time. You ready? Ratio test. It's going to get messy, but everything's going to work out real nice. Limit n goes to infinity. Let's see if you can keep up with what I'm doing here. I've got to do n plus 1 into all of these, right? So I'm going to do this with n plus 1 in divided by this by itself. Then I'm going to flip that one, the one on the bottom up. I'm going to do it all at one time. -1 to the n plus 1, x to the 2, be careful, n plus 1. Notice how I put this right here, this n is replaced with n plus 1. It has to be in parentheses. Over 2 to the 2, again, n plus 1 here. And then I have, real careful with this, n plus 1 factorial, that whole thing squared. That's n plus 1 plugged into everything. Then divide this by this, which is the same as multiplying by the reciprocal. 2 to the 2n, n factorial squared, -1 to the n, x to the 2n. That looks pretty bad. All right, let's get rid of some stuff we don't need. Those we don't need. Absolute value is going to take care of those. Now, oh yeah, they're gone. The negative ones to powers, they're gone. Yep. This, just keep in mind, this right here is 2n plus 2, right? This one is also 2n plus 2. Yeah? So watch what I do here. I'm going to rewrite x to the 2n plus 2 as x to the 2n times x to the 2. What's still on top? I'm going to put them all together. 2 to the 2n, and then n factorial squared. Yeah? Okay. Over this right here. 2 to the 2n plus 2 is going to be 4. Well, yeah. Can I just do 2 to the 2n times 2 to the 2, and then I'll turn it into a 4. That okay? What's still here? N plus 1 factorial squared. How about this? N plus 1 times n factorial all squared. This in here is n plus 1 factorial, right? Then I'm going to square the whole thing. I still have down here x to the 2n. This x to the 2n cancels with this one. 2 to the 2n cancels with this one. Now, what can I do with this n plus 1 times n factorial, the whole thing squared? Can I square each one? Yes, because there's multiplication between them. I can't do it if it's addition. So just keep in mind, this right here is n plus 1 squared times n factorial squared. That's what that is, right? So what cancels? The n factorial squared. Pretty good, pretty good. Things are working out pretty smoothly here. I know it looks messy, but continuing my limit. Limit n goes to infinity. Okay. Let's keep the x's and the n's separated. Let's start with the n stuff. What do I have that has n's in it? I have just this right here, right? That's the only thing with an n in it, and it's on the bottom. I also have a 4 here, don't I? I'm going to put that with the n's. I have 1 over 4 n plus 1 squared. Agreed? Then I still have the x squared, but I'm going to keep it separated. So I'm going to say times x squared, absolute value. Yeah? Am I missing anything? Does that account for everything? Okay. Let's ask ourselves this question. What is it going to take to keep this less than 1? Because that's what I need for convergence, right? So if you come in here and you fix an x, right? If I take this and I fix it, what's going to happen? What's going to go? This right here is going to 0. So it doesn't matter what this is, right? This could be a cajillion, right? A billion, whatever you want. This is going to 0. 0 times, it's going to multiply by something so small, this is not going to matter. And this thing will eventually get less than 1 because I'm going to infinity on n.
So
yes?
X is X always going to be fixed? It can't be like infinity?
X cannot be infinity. That is correct. X has got to be a real number because remember, x is like the input of the function, so it's got to be a real number. What does this mean? It converges always, right? Regardless of x. So our conclusion is that this converges on negative infinity to infinity. Still have 2 minutes. There was one more that I was able to get to on my other class, which I think for you, I'll put it up here for you, and then you can mess with it yourself. Although I still have a minute. How about this one? Sum n equals 0 to infinity, 2n plus 3, 2x plus 3, I'm sorry. 2x plus 3 over n. And I forgot to raise the 2x plus 3 to the n. Is that a power series? Does it look like sum c sub n x minus a to the n? Yes, here's what you can do to convince yourself. You can do 2x plus 3 halves, right? Factor out a 2 to the n over n. Is that the same? Yes? And then do 2 to the n x plus 3 halves to the n all over what? N? Is that the same? This is c sub n, x minus a. What's a here? Negative 3 halves, right? This is a power series. We could check to see if it converges by running a ratio test. Now, I'll pick up right here next class, all right? I don't want to keep you on any longer. I'm not going to give you any homework for this section. Get caught up, because I know probably with that take-home test, you probably didn't have a chance to really get caught up. So get caught up with